All right, today we're going to dive into a really fascinating paper from Hatamizadeh and his team. They've developed a new AI that can map out brain tumors with, honestly, mind-blowing precision. And this isn't just about cool tech. It's a story about teaching a machine to see something more than just pixels, to see the life-or-death context hidden inside an image.
So let's start with a really important question. How do you map a tumor inside a human brain and do it with perfect accuracy? You know, this isn't just some abstract technical problem. It's deeply human. For a doctor, for a patient, being able to see the exact size, the shape, the location of a tumor from an MRI, that's absolutely the first, most critical step in saving a life.
I mean, think about it. Literally everything that comes next. Are we doing surgery? What's the plan for radiation therapy? All of it hinges on getting that map just right. It is, without a doubt, the foundation for the entire fight against brain cancer.
So the tool that lets us do this comes from the world of computer vision. And to really get why this new paper is such a big deal, we've got to understand the specific and honestly super complex task this AI was built for.
Okay, so what is this task? Well, it's got a technical name, semantic segmentation. But what does that really mean? In plain English, it's about teaching a computer to do more than just see an image. We want it to understand what every single pixel in that image actually is.
Here's a great way to think about it. Imagine you have a super high-tech 3D coloring book of a brain scan. Your job is to color it in, pixel by pixel. You'd color all the healthy tissue, say blue, the skull gray, and then, most importantly, you'd color every single bit of the tumor red. That's exactly what this AI is being trained to do, but automatically and perfectly.
Okay, so for a long time, there's been a sort of champion, a go-to tool for this exact job. And it's powerful, for sure, but there's a catch. It has a fundamental flaw, a blind spot. You could almost call it a kind of tunnel vision.
These models are called fully convolutional neural networks, or FCNNs for short. They pretty much became the industry standard. And you can think of them like tiny digital detectives, right? They take a magnifying glass to the image, scanning it piece by piece, and they get really, really good at spotting small local patterns and textures.
So if they're the standard and they're so good at details, what's the problem? What's the blind spot? What on earth could these powerful networks be missing?
And here it is, the core of the problem. Those FCNNs, with their magnifying glass, are amazing at seeing the tiny details up close, the local view. But they totally miss the forest for the trees. They just can't see the big picture. Now, on the other hand, you have transformers. This is the tech that completely changed the game for language AI, right? Well, they work differently. They look at every part of an image in relation to every other part, all at once. This gives them a global view.
So what does this mean in the real world, for a real patient? Well, it's a huge deal, because brain tumors aren't one size fits all. Some are tiny and neat, but others are massive and they sprawl all over the place. An AI that can only see that local view, it just gets lost. It struggles to trace the full boundary of a big, weirdly shaped tumor.
So what we really need is an AI that can do both, right? One that can see the tiny pixel-level details and the giant overall picture. And that brings us right to the brilliant innovation at the heart of this paper.
So what did they come up with? It's called Swin UNETR. And the name itself is actually a huge clue to how it works. It's a hybrid. It smashes together a Swin transformer, that's the part that gets the global, big picture view, with a UNet architecture, which is a classic, super powerful FCNN design that's great at all those local details. And you can see where they got the idea. They looked at the insane success of transformers in other areas, like language, and they basically asked a really smart question. Hey, what if we could give a medical imaging network that same incredible power to see the whole picture?
So here's how it works, and it's actually a really elegant two-part system. First, you feed the MRI scans into what's called an encoder. That's the Swin transformer's job. It looks at the whole 3D scan and pulls out the big picture information. Then, that high-level understanding gets handed off to the decoder. And this is where the FCNM part comes in. It takes that big picture context and uses it as a guide to rebuild a perfect pixel-by-pixel map of the tumor.
So, what you get is literally the best of both worlds. The transformer gives it the global vision that the FCNN was always missing, and the FCNN part handles the super precise, fine-grained mapping that it's always been amazing at. They cover for each other's weaknesses perfectly. It's a true dream team.
Okay,
So it sounds like a fantastic idea on paper, right? But the real question is, does it actually work better in the real world? Well, to find out, the team didn't just write a paper. They threw their model into a super tough, high-stakes competition.
They entered Swin UNET into something called the BRATS Challenge. That stands for Brain Tumor Segmentation. And you should know, this is like the Olympics for this kind of AI. It's a huge deal. All the top models from labs all over the world compete on the exact same set of data to see which one is the absolute best at mapping these tumors.
And how did they do? Well, it was a massive success. The paper puts it modestly, saying it ranked among the top performing approaches. Let me tell you, in a competition this fierce, that is a huge win.
So this wasn't just about winning a competition. It was a total validation of their whole idea. It proved that this hybrid approach, this fusion of big-picture vision and tiny detail precision, isn't just a clever thought experiment. It delivers state-of-the-art results. It's a genuine leap forward for medical imaging.
All right, so let's just pull this all together for a second. We started with this massive challenge. How do you accurately map a brain tumor? We saw the old way, the FCNNs, were good at details but couldn't see the big picture. Then came the solution, Swin UNETR. This awesome hybrid model that combines the transformer's global view with the FCNN's local precision. And the result? A model that's now proven to be one of the best on the planet at this incredibly important task.
You know, what's so cool about this is that it shows how taking an idea from one part of AI, like the transformers from language, and applying it somewhere totally different, like medicine, can create these powerful new tools. It really makes you wonder, right? As these models get even better at seeing and understanding our world, what other huge medical challenges are they going to help us crack next?